Welcome to the Explainer. Today, we're going to dive into a really clever logic puzzle from a linear algebra exam. But, this isn't just about getting a good grade. It's about pulling back the curtain on the hidden rules that run everything from your GPS to the graphics in video games. We're about to do some real detective work with vectors and matrices, and trust me, we're going to uncover some surprising truths. Okay, so here's our game plan. First, we're going to crack a puzzle that involves 3 different vector equations. Then, we'll take what we learned and put on our detective hats to figure out which of 2 bold claims about matrices is actually true and which one is totally false. Let's jump in. So, here's the setup. We've got 3 equations, but we only get clues about the first 2. Our mission, if we choose to accept it, is to use that very limited information to figure out the fate of that mysterious third equation. Right? Here's the heart of the puzzle. We've got one equation with way too many solutions, an infinite number of them, and another one that has exactly one, a unique solution. So the big question is, what happens when we start mixing and matching their parts? What can these 2 complete opposites tell us about our third equation? Okay, let's start our investigation with that first clue, infinite solutions. Now, this isn't just some mathematical oddity. It's a massive tell. It's a clue that points to something really fundamental about the vectors making up the equation. So if you've ever studied a little linear algebra, the phrase infinite solutions should be like a giant flashing neon sign. It's telling you that your system has some fat to trim, that there's a redundancy baked right in. It's kind of like having a whole keychain full of keys that all open the exact same door. You really don't need all of them.
And that redundancy, well, it has a name, linear dependence. What it basically means is that at least one of your vectors isn't really pulling its own weight. It's just a mashup of the other vectors. It's not adding any new information, any new direction to the whole set.
So, our first big deduction is this. Seeing infinite solutions immediately tells us that the larger set of vectors is linearly dependent. Let's file that away as we look at our next clue. Now, for clue number 2, which you'll see is the complete opposite of the first. And it's actually in that sharp contrast that we're going to find the key to this whole puzzle. A unique solution. Now, this tells us we're working with a system that is perfectly efficient, perfectly tuned. It's like a key that fits a lock perfectly. There is only one way to get it to work. And the math term for that perfect efficiency is linear independence. It means every single vector in this set is absolutely essential. Each one points in a unique direction that you can't get to by just mixing the others. They're all fundamental building blocks. And there's our second big takeaway. The smaller set of vectors is linearly independent. So now we have these 2 crucial opposing clues. The big set is redundant, but the smaller set, just one vector shy, is perfectly efficient. Okay, we've got our clues. We know the big group of vectors is dependent, and the smaller group is independent. It's time. Let's put these pieces together and crack the case of our third equation. This right here lays out the whole chain of logic. I mean, think about it. If you have this perfectly efficient, independent set of vectors, and then you add just one more vector and suddenly the whole group becomes redundant, well, that new vector has to be the culprit, right? It's the source of the redundancy. This means V sub k can be built just by combining the other vectors. And if that's true, it leads to the amazing conclusion that our target vector u can also be reached using only that smaller independent set. In other words, u is in what we call the span of the smaller set. It's reachable. And because that smaller set of vectors is linearly independent, there can only be one single way to combine them to get to u. Case closed. That third equation has a unique solution. All right, we just sharpened our deductive skills on those vectors. Let's take those skills and apply them to a totally new puzzle, this time involving matrices. We're told that the product of 3 matrices, A, C, and B, is invertible. And our job is to test 2 claims that come out of that one little fact. Okay, here are the 2 claims we've got to investigate. The first one suggests that if the matrix in the middle, C, is invertible, then the product of A and B also has to be invertible. The second claim, well, it makes this surprising link between whether C can be inverted and the actual dimensions of the matrices. Now, one of these is true and one is false. Let's find out which is which. So this first claim, it seems plausible, doesn't it? If the matrix C, sandwiched in the middle, is invertible, it just feels like that property should extend to its neighbors, A and B. It's a really tempting idea. But, in math, a hunch isn't enough. We need proof. And boom! This slide shows us exactly why that first claim is dead wrong. All it takes is one clever counterexample to just completely demolish the whole argument. As you can see, we built some matrices where C is invertible, and the whole product, ACB, is invertible. But look what happens when we multiply just A and B together. We get the zero matrix, which is about as non-invertible as you can get. So yeah, claim 1 is officially busted.
All right, so claim 1 was a dud. Let's turn our attention to claim 2. This one feels different. It's not just about properties like invertibility, it's about the very shape and size of the matrices. It's connecting that property to their dimensions, n and m. This feels like a much deeper, more fundamental question.
To solve this second claim, we're going to need a more powerful tool than just hunting for a counterexample. We need something that tells us about the deep, fundamental properties of a matrix. And that tool is called matrix rank. You can kind of think of a matrix's rank as a measure of its information content, or how many independent directions it really captures.
Okay, let's walk through this proof step by step. First things first, we know ACB is an invertible m by m matrix. That's a given. By definition, that means its rank has to be m. Got it. Next, we use a super important property of rank. The rank of a product of matrices can never be bigger than the rank of any of the individual matrices in that product. So the rank of ACB has to be less than or equal to the rank of C. Now let's put those two things together. We get m is less than or equal to the rank of C. But wait, there's more. We were told C is not invertible. For an n by n matrix like C, that means its rank must be less than n. So now we have this beautiful chain of inequalities. M is less than or equal to the rank of C, and the rank of C is strictly less than n. You put it all together, and what do you get? M is less than n.
And that simple little inequality, m less than n, proves that claim 2 is absolutely true. So there you have it, our final verdict. The first claim was false, and we took it down with a single counterexample. The second claim was true, and we proved it using a fundamental concept of matrices, their rank.
So why do we care about any of this? Because out here in the real world, we constantly need our systems to give us one and only one right answer. Whether you're designing a bridge and you need it to be stable, or you're writing code for a GPS that has to find a single location, or even creating an encryption algorithm that only has one key. The principles of linear independence and invertibility are the bedrock that guarantees you get a unique, predictable, reliable solution. And that kind of leaves us with a final thought to chew on. When you're facing a problem in your own life, and it seems to have infinite confusing answers or maybe no answer at all, could it be that the problem isn't out there in the world, but with your own fundamental assumptions? With your own personal basis vectors? Just something to think about. Thanks for joining this explainer.